bit different spin to my presentation versus others that you've seen, because being the chair of the session, I got to see everybody's papers, and I decided that mine was kind of too much like some of the others that you're going to hear later in the afternoon. So what I tried to do was look at a little bit different aspect of some of the issues that we face in the workplace. We've talked a lot about fume and now some EPA regulations. What I was going to try to introduce, and I think again some of the other speakers later on will be emphasizing this as well, is looking at the welding process to optimize the process. And there are a variety of things that we can look at, but often people don't understand what all of them are. Kathy mentioned too that part of this EPA regulation is looking at optimizing the process. Have you looked at the consumable to see is there some consumable that may generate less fume? You looked at the process. And that's kind of what I'm going to touch on here and show you a specific example of an area that we have looked at to do some of this optimization. So typically when we look at optimizing a process, we're often focused on the monetary aspects. We're looking at, deposition efficiency. Can we improve that? Can we get a higher deposition rate? Basically what we're looking at are the factors that affect the cost of the operation, because what we want to do is develop some savings down here. So one of the other things that we don't consider, and in many of the welding done in North America, in Europe, the cost is in not so much the consumables, but in the labor and overhead cost. So that's obviously affected by deposition rate, welding speed, but also one of the things is how much post-weld processing do we need to do? What's the impact of welding fume on the cost of on the overhead operations of our facility? So what we're going to just take a look at a couple of the other factors that may affect. We've heard about fume. You'll hear later, and you've heard a little bit already this morning, just changing the shielding gas for a gas-shielded welding process can lower the fume from CO2 to 25% CO2 in argon, 15% CO2 in argon. So as we lower the CO2 content of a shielding gas, it affects the amount of welding fume that's generated. So, that's one thing we could look at. The photo, this is a little bit hard to see from a distance, but here we're talking about using a conventional welding supply with 100% CO2 shielding. This is a lap fillet weld. What you can't see too easily here is that there's a fair amount of spatter along the edges of the weld. The edge of the weld is kind of crowned, so if you needed a smooth flat surface, it might require some grinding. We're here a different type of process, a controlled metal transfer process, virtually a spatterless process, a flat weld bead. So again, a little bit less post-weld processing would affect this operation. So spatter level, bead shape also affect the productivity and the cost of the welding operation. So what we're going to do is just walk through a little bit of some process optimization steps that you might consider. Typically for a given operation, we're going to have a material type, a thickness, surface condition that we're going to have to deal with. It's the material we have to utilize in our facility. Most typically, you'll have selected a welding consumable, whether it may, I'll say at least a consumable type, maybe a flux cord wire, a solid wire, could be a stick electrode, but we'll focus on gas-shielded processes here. And typically, you'll have decided on the process based on the equipment. If it's flux cord or solid wire, it could be a globular type transfer depending on the shielding gases you use. With solid wire, it could be spray transfer, it could be short circuiting type transfer, it could be pulsed metal transfer. So the equipment will obviously determine to a degree the process we can use. But some of the variables we don't often look at, are the shielding gases. I mentioned earlier it could affect fume generation. The welding power source, again, with the technology that's available today. You go down on the show floor and you look at the major suppliers of welding equipment. And the technology that's available in a power supply today, you literally can tailor the output of that power supply to a specific welding process, to a specific welding material. And I'll show you a couple examples of that. And then lastly, we talked about optimizing the performance. Are you using the appropriate current levels, voltage levels, and whatever for the actual application, or can those be adjusted to get better performance? So the example that I'm going to use is one, if any of you have welded high nickel alloys, sometimes stainless steels, but typically high nickel alloys are very challenging materials to weld. One of the reasons is the weld pool is very viscous. It's not fluid. It doesn't want to flow well. So you tend to get weld beads that are not very well wet out. Travel speeds are slow because, again, the material doesn't want to flow. Typically, in other welding operations, you might add something like oxygen or CO2 to a shielding gas to improve the fluidity of the weld pool. But with nickel, you get a very tenacious oxide on the surface that actually makes it harder to get the material to flow. So there's some real limitations as to what you can do. And it has very poor transfer characteristics. It tends to be pretty spattery, and again, weld bead shape is not real good. So we looked at this area as to see what can we do with some of those variables I mentioned, shielding gas, power supply, parameter optimization, to make this welding process better, and how does that affect, process optimization is, from a cost standpoint, and also from some of the other things that we talked about. So the desired result is obviously we want a good quality weld metal, and we'd like to minimize the amount of post-weld processing. So that's grinding, defect removal, anything like that. And obviously to be more productive if we could get travel speeds, in fact, higher. So the idea here is, can we meet the technical goals, the actual goal of fabricating a material out of these nickel alloys while improving the overall work environment, which means from a welding fume standpoint, from a noise standpoint, from a dust and dirt standpoint. So we're going to look at the shielding gas first. For those of you, many of you know if you've used a gas-shielded welding process, typically what is the shielding gas supposed to do? It's supposed to protect the molten material from being exposed to the atmosphere. But what I'll show you in a minute is that actually the shielding gas can control a whole host of variables. Type of metal transfer you get, the amount of spatter that you might generate in the welding operation, all kinds of factors related to the appearance of the weld bead. So by matching the shielding gas selection with the consumable and the process, we can start to affect some of this optimization. Just to give you a little bit of background, I know people love numbers and tables like this, but just to highlight a couple of things. The reason why different gases are used in welding is because they have different properties. They have different effects on the welding process. Good example here is argon and helium. Why do we use argon or helium or hydrogen in some cases? And when we're talking about stainless steels and nickel, we can use some hydrogen because it doesn't have a negative effect on the properties of the weld. But one of the reasons here is that the thermal conductivity of the gas, how much of the energy is generated in the arc gets transmitted to the base material. This relates to fluidity, this relates to travel speed, this relates to actually controlling metal transfer. Argon is a much less, it has a much lower thermal conductivity, but it has an advantage down here of this ionization potential relates to how easily can you start an arc when you're using an argon-based shielding gas. Helium is much higher, it's much harder to start an arc. Arc starts typically can relate to defects. Poor arc starts can relate to defects, which can relate to having to remove those defects, can relate to spatter, again, more post-weld processing. So there are different properties of the gases that we take advantage of to optimize a welding situation. So basically we use mixtures of gases because we try to balance the properties of the gases. Argon is, inert, easy arc starting characteristics. Helium has that increased heat transferability, also inert. We use materials like CO2, or carbon dioxide and oxygen to increase the stability of the welding operation, often to increase the fluidity of the weld pool in carbon steel welding and in other materials. And then where we can use hydrogen as well. One of the interesting things about hydrogen is not only does it have good heat transfer characteristics, but it can remove oxides. It's a reducing gas, so it reacts with oxides on the surface to get a cleaner weld with less oxide, again, which could relate to less post-weld processing. This particular example, what I'm going to show you is in this optimization, we looked at a variety of different shielding gases. Some of them, just pure argon, argon with a little bit of helium and some CO2, argon with more helium and a small percentages of CO2, and here's one with some hydrogen. These two have hydrogen. And we'll just show you, I'm not going to go into a lot of detail, but this, we were looking at this again, variety of blends to see how can we optimize this situation. And just, again, to show you what some of the shielding gas can do. Again, if you look at this is all done under similar welding conditions. You look at different bead-shaped characteristics you get by just changing some of the gas blends. Different penetration, different surface characteristics. Some are flatter, some have it's looking at just the cross-section, you don't get a full picture of what the weld bead looks like. Like this argon looks pretty good, but actually the surface is fairly rough if you looked at the surface of the weld bead. But again, the shielding gas affecting some of the characteristics of the welding process. Okay, now, shielding gas is one thing, but what about the type of metal transfer that we're using? What about the power supply characteristics? Well, one of the most flexible types of metal transfer that we can use today is pulsed MIG transfer. So this is a spray type transfer where you get discrete droplets of metal transferred at a fixed frequency. So it's like the conventional spray transfer, which you get in argon-based shielding gases with solid wire welding and metal core arc welding, where you get a stream of droplets. Here you get a discrete number of droplets. And this is done by a power supply changing current levels from a low level that maintains the arc to a higher level that provides enough energy to transfer droplets. But what this process begins to allow you to do now is you can now control how those droplets are squeezed off the end of the wire and transferred. And now again, control things like spatter and bead shape with power supply characteristics. These are, for pulsed MIG welding, these are the characteristics you can control. This peak current, which is the maximum current that squeezes off the droplet, the background current that establishes the basic arc length and heat input of the system. The pulsing frequency relates to how many times that current level goes up to a high level and squeezes off a droplet. And then some other characteristics of the pulse, how wide and how high. Again, the amount of energy you put into the system. And now this is related now to the types of materials that we're trying to use. In this particular case, where we're looking at an example here of, in many power supplies, pulsed power supplies, they build a specific electronic waveform into the power supply for a specific type of material. So you'll find one for carbon steel with a certain shielding gas. You may find another one for carbon steel with another type of shielding gas. You'll find them for stainless steels. You'll find them for aluminum. So again, the power supply is helping to tailor and optimize the system. Here what we're looking at is a standard power supply or a pulse power supply with a waveform that was developed for stainless steel. And we're using 100% argon, and you can see this bead on plate. The bead's fairly, has a fairly high crown, not too much penetration. And this is kind of what the waveform looked like. taking another type of waveform developed for specific types of nickel alloys. What you can't see here is a little bit of shadowing, but the bead is actually a little bit flatter but has much deeper penetration. So again, by changing this waveform using the same materials, we've affected the bead shape. What shielding gas changes and waveforms also relate to are arc stability. And arc stability often relates to spatter and control of the welding process. Here what we're again looking at is a standard stainless steel waveform with this particular shielding gas, the multi-component shielding gas. And here we're looking at this same material with this different waveform. So again, here's what the weld bead looks like with the stainless waveform. Here's with this Inconel or nickel alloy. You can see the arc stability is much better than it is up here. What's happened here is the frequency of this pulsing has changed from 135 to 97. The height of the peak has gone up. It's a higher peak, but less frequent peaks. So again, tailoring this waveform to a specific material now begins to optimize the welding system for this particularly difficult to weld alloy. This is just to give you a little bit of a visual picture. Again, here's the prototype waveform. Actually, what you can't tell here is that the bead shape is not too bad, but it's actually the surface is a lot rougher than this particular here. So particularly with these high alloy specialty materials, bead shape and surface condition are very important. And if they're not flat, if they're fairly rough, they require post-weld grinding and other processing. So I'm going to just skip that one. So this is, one of the things you get to with process optimization, other than fume reduction, which is obviously a good goal, is that when you have less post-weld, less need to grind, there's less grinding dust, reduced noise. Some numbers that I had just found, typical, they said in a fabricating shop, the typical noise level is 85 to 95 dB is kind of typical. Gouging can increase. I'm surprised it isn't even louder than this. If you've done arc gouging, you know that it's very loud. But use of a grinder is also a significant noise polluter. So the fact that you could reduce the amount of grinding required would have a significant impact on noise levels in the workshop. One of the other things that we had run into, I had worked with a customer actually on a welding related problem. This is actually the back side of a stainless steel dump truck. One of these large trucks that you see with stainless steel containers in the back. But they're welding stiffeners or pieces of material to stiffen the surface of the large truck containers. But in welding, from welding these stiffeners on, the outside or the side that you would see, say, from the street, discolors. And so this is what it would look like. So because they would get this heat tinted surface, they had to use pickling chemicals to remove the oxide to improve the appearance. As a result of using those chemicals, they were having a disposal issue with EPA because of disposal of these chemicals. So they were looking for an alternative way to avoid use of chemicals. And so actually over here, it's not perfect, but this was done with just using some nitrogen on the back side of the weld through a little kind of a diffuser to just shield that back side of the weld. And as a result, actually the shielding wasn't on when the arc first started, but it essentially eliminated that heat tint surface. So, again, another concept, another way to look at optimization to eliminate the use of some of these chemicals like that. We mentioned earlier that post-welding shielding gas selection can affect the fume generation. This is just a comparison of conventional spray arc welding with stainless steels versus pulsed arc welding with some different shielding gas blends. And as you can see, basically pulsed welding reduces the fume level from even conventional spray welding, which is already pretty low, but it can reduce the fume by 25 to 50%. So again, process selection, what Kathy talked about for this EPA-related documentation is what am I doing to reduce control fume or control emissions in the welding process.
Is that argon O2 mix, is that 97.3?
Actually, in that case, it's just 2% oxygen. Yeah, actually, argon oxygen gives you the lowest fume levels of any types of shielding gases because the fume is definitely affected by the CO2 content. Argon oxygen is limiting for some other reasons, but for fume, it's particularly, it's the best. So, just in summary, looking at your welding process, not only can you look at fume levels, you can look at how can I minimize other processing steps that I need to take, whether it's spatter removal, whether it's weld bead shaping, whether it's removal of oxide. There's a variety of ways of looking at controlling the welding process through consumable selection, through power supply selection, and the capabilities of the power supply. So, here, mixtures of gases can be used to improve the welding characteristics of a system. Types of power supplies can, and optimization of variables. And basically, I think you have a pretty good opportunity to look at completing both your technical goals and these other, and trying to also improve the work environment that you're operating in. Oops, no, I did that same thing. And so, we think and basically all these things, often what's really surprising is that even when you institute some of these things that look like they will cost you money, in effect, when you look at the overall cost of welding, they actually reduce the cost of the welding operation. So that's, again, just some other things for you to think about. We'll be hearing more later in the program from some other speakers more focused on some fume reduction and parameter control. So hopefully this helps give you an additional viewpoint.